This conference will now be recorded.
Mary Beth, can you still hear me?
Yes.
Okay. We're going to get started here in about 1 minute.
Hey, Steve, this is Nima speaking. Can I send my presentation to you, or can I share it here?
We'll let you share it. We'll do a little transition between talks here. So if you just want to hold on to it or have it on your screen ready to go.
Sure.
Okay, I think we'll go ahead and get started. This is Steve Greb, the director of AquaWatch. Well, good morning, good afternoon, or good evening, as the case may be. Whether this is your first or fifth telecon today, we welcome you all to this community discussion of analysis-ready data. So I hope you can sit back and, as we were just talking about, grab your appropriate beverage for whatever time of day it is where you're at, and I'm hoping for a fruitful discussion here. I'm not going to spend a lot of time on the introductions. I'll leave it to the speakers themselves to introduce themselves. Today we're going to learn a little bit about ARDs, the activities and issues surrounding ARDs, particularly in the aquatic side of things, and then spend the remaining time both answering questions and maybe to start identifying community needs and identify tasks for the community, and whether it be reviewing the product family specifications, which we might hear about here shortly, delineating differences in the ARD products, or just helping to define a pathway forward. So I ask if you have questions or comments to please type them in the chat box. We'll be monitoring that. And maybe as we transition between speakers, we might have time for a brief question or two. As far as agenda repair, Andrew Tyler has joined us and will be leading the discussion under agenda item number 5. So with that, I'm going to turn it over to both Rob Woodcock and Brian Kelo. I believe Brian's going to give the presentation on the concept of ARD and why we need it. Gentlemen.
Hi, who wants it, Brian or Rob? Who wants control?
It should be Brian, and I'm not set up to fill in for Brian. So, Brian, are you out there? We don't appear to have Brian.
He doesn't appear to be on the participant list.
Well, this is an auspicious start.
Can you share the presentation?
I don't have the presentation.
I can get it in a second here.
Here, let me send it to you.
Yes, it would appear the iPad cannot share.
I just made Steve grab the presenter, so he can drive for you. Steve, are you out there?
Yeah.
Okay, we just need an update on what you're doing.
Okay. How's that? Rob?
Not visible at my end yet.
Just click share screen. We're still not seeing your screen, Steve.
Okay.
Yes.
Great.
Just ask me when you want to switch slides.
No problem. All right, so sorry about that, everybody. That Brian obviously is having some form of technical difficulty connecting, and he was going to be giving this presentation because it's quite early in the morning here. So if you hear some background noise, it's just my family going about normal family things in the morning. If you can move to the next slide. So this presentation is really just about the quick introduction to the concept of ARD and why we actually need it. And ARD stands for Analysis Ready Data. It's what we're finding is across the CEOS agencies, across the group on Earth observation and industry as well, the proliferation of Earth observation data, the availability of it in the cloud, and the uses you can put it to have gone up very dramatically in recent years. But what this has done is it's made Earth observation data is no longer just a specialist science exploring an issue. It's actually now being used for decision making, including in areas like water quality and water usage monitoring and so forth. And this puts pressure on the front end of the pipeline where satellite data collected needs to be corrected for the atmosphere, for the terrain, for clouds and so forth. And that can be quite a scientific specialist area. ARD is about actually having that work done prior to publication so that the people are actually getting data that is ready for analysis. They don't have to do that earlier stage and more specialist calculation. Within CEOS, the Land Surface Imaging Group has been working on CS analysis ready data for land. This sets up a minimum set of specifications for processing for that land-based products. And there are a few product family specifications for land at the moment around surface reflectance, temperature, and normalized backscatter from radar. And they're working on some additional ones. Now, the ARD work itself is coordinated across all of CEOS, the Community on Earth Observation Satellites, and connected to many of our groups. Their acronyms are all listed there. The reason for this is because, of course, you do analysis-ready data for land, but we also need analysis-ready data for water and oceans and atmospheres. And so there's a range of products that need to be created, and each of these groups add to that. And then there's groups like Working Group on Calibration and Validation that are used to help provide procedures and methodologies for validating that data is in fact meeting the specifications. And then there's groups like the Working Group on Information Systems and Services that help make that data discoverable, or they provide a way of putting that data into an appropriate format, file format for use in the cloud and so forth. So what we'll be focusing on during today's discussion is really this product family specification. It's to do with the geophysical measurements. So if we move to the next slide. So ARD itself is then providing that easier access to more readily used data. So it removes the data preparation burden from third parties. You don't have to be a specialist in atmospheric correction and BRDF to be able to use it. In particular, it's promoting data quality, and this one is very important to the water world. Water does not reflect optical light very well. So you tend to have water reflection being within the kind of signal to noise ratio of the satellite sensor itself. So there's very important to get that right with water. We want the consistency among the different approaches to doing the corrections. And more importantly, we want the products that are derived from this to be consistent. So water quality and water in general tends to be a cross-jurisdictional issue. And so you need to want to have products that are being produced effectively each time. And today's discussion is about making sure that the underlying data is corrected to the same kind of standards so that the measurements are more comparable, and we don't end up having discussions about things that aren't actually real when comparing reports. The other thing it does is, because we're removing the burden for lots of people, we end up improving the computational efficiency. So why do we need aquatic ARD? Basically, there's an increased interest in water quality, and we have a lot of people producing water quality algorithms or water quality products, but the noise, the radiant signal is very low compared to that of land. So we need to have a fairly consistent way of communicating not only the geophysical measurements that are corrected consistently, but also their quality targets as well to help improve our science products. And that would be what Brian would say if he was here.
I think he has joined us now.
Yeah, I'm here. I was trying to use the link that was on the PDF file, which was to a Zoho meeting, and I was waiting all by myself and nobody arrived. And then I figured out I must be at the wrong meeting. So my apologies. And eventually I thank Paul. I think, Paul, you sent me an email and gave me the the GoToMeeting link. So my apologies to everybody. I was on a different link.
No worries,
All
Brian.
right.
Looks like
Okay.
you covered it all quite well, Rob. Sorry to keep you awake.
Okay, well, thank you. Thanks, Rob and Brian, and apologies to Brian. This is a screw up on our part. So we're going to move right along here and move on to the Landsat 8, looking at some of the current status ARD products for aquatic systems. Is there a quick question for Rob or Brian?
I saw a question in the chat box, and I put the CIOST link to ARD in there. There's a lot of information there if anybody wants to visit that. CIOST.org/ARD.
Still, thank you for that reply. Still very centered into the land, so the CIOS, ARD for land. And my question was in the presentation, I believe it was mentioned that there are other R&D initiatives for other usage, and in particular this webinar is about the aquatic one. But my question is, are there other initiatives that are not the aquatic or the land?
No, we've just really started this within the last year. So we started with land because that's the one that the community most desperately needed with the proliferation of the Landsat and Sentinel data out there and it being processed in various formats. So that was where the need existed first. And now we're starting to see this pick up intensity and interest, and therefore we're expanding. So this aquatic ARD is the first one that touches something other than land, and there is a lot of discussion out there about adapting this and moving this towards other data sets in land, ocean, and atmosphere.
Okay, thank you. I understand.
So Nima, is Steve Laban presenting now?
Yes.
Okay, I'm sorry. I made you presenter. Just a second.
Okay, can you see that?
Yeah.
You can. You may want to go into full screen. Yeah, click on the display settings and choose the other option. Yeah, swap presenter view. Perfect.
How does that look?
Perfect.
Very good. Okay, should I just start? Did
Please.
Nima already talk?
No, he hasn't.
Oh, okay. So what I thought I'd mention or talk to real quick is some of the work that's going on within the CIOS community, the land surface imaging virtual constellation, product family specification work related to aquatic reflectance. And I'm one of the co-leads in this team within CIOS. And just a little bit of a background chart on CIOS and land surface imaging. If you're not familiar, and CIOS really playing this space component to GEOS and supporting the GEO or Group on Earth Observation tasks. Within that, within CIOS, LSI is really working on several things, but in this context, on the promotion of common standards and land surface imaging products that support some of these needs, in particular on aquatic needs. I'm going to get into a little bit here. So one of the things that's been done within this group, Land Surface Imaging Virtual Constellation, is to create what we've called a CARD4L, the CIOS Analysis Ready Data for Land framework. And this framework basically starts at a top level with a basic definition. Really what it's trying to do is create a minimum set of requirements for organizing data to some minimum levels so that little additional user efforts required and supporting at least some basic levels of interoperability. And within that context, several specifications have already been developed and endorsed within this group. Several optical ones, including one for surface reflectance and another for surface temperature. And then now most recently also endorsed normalized radar backscatter SAR specification, as well as one for polarimetric radar. Several other radar specifications are in work. LiDAR is under consideration. The one I want to talk about today is really this one on aquatic reflectance. And Nima is going to be talking about some of the product and algorithm work that's being done in support of this, and these are kind of being worked in parallel. Basically, the thought is that we could get to some common definition specifications for aquatic reflectance products, that the providers of these data sets would then self-assess against these specifications, and another group within CIOS called the Working Group on Calibration Validation would peer review then these assessments for at the end would be a card for L compliance stamp, so this product meeting all of these specifications. Where are we at today? And this is really just as a high level, trying to give some overview, but we've been working on an initial draft of an aquatic reflectance specification. Chris Barnes and our team has been working that. This specification started with the surface reflectance specification that's already been endorsed, and making additional changes, modifications to that specification to accommodate special needs for aquatic products. So we've been meeting also with Nima, who's going to be briefing here next, on the margins of the Lancet Science Team meeting we had back in February to get an initial kind of a check on the specification. Been working with Nima, Chris, and I on refining that specification since then, and hopefully by the end of the month we're very close to having an initial draft of the specification, such that we would go into the next step, which is a science expert review panel of that specification. And we've already received a few names that are interested in being part of this review. You can see those on there, and we're open and welcoming additional participants. So you can contact me after this if you're interested. Following that step, hopefully by the end of July, we'll be able to do a final tech edit and distributing of this specification for review and then endorsement by September. That's our goal. And I think that's my last chart, just to kind of give a quick overview of what we're doing from a specification perspective, and then I think I can hand it over to Nima, and he'll talk about the actual algorithm and product development side of the house.
Steve, you want to go ahead and show my slide? That may be easier.
Absolutely.
You have them. Okay, good.
Yep, I'll just get them. Is that showing up okay?
In
other mode again. Here, let me go.
If you do a okay, thanks, Steve. So yeah, my name is Nima Pahlavan. I work for SSAI, based at NASA Goddard Space Flight Center. I would like to continue with describing a little bit of a backbone of what's included in the USGS ARROS processing to generate aquatic reflectance products. These products are provisional, they are on demand, and they could be essentially requested by end users, and they will be essentially provided back to the end users when they become available through the processing system. So CDAS, the CWIFS data analysis system, is the atmospheric correction processor that is used to generate these aquatic reflectance products. This processor was initially developed for processing CWIFS images over open ocean and moderately turbid coastal waters. The initial discussion for incorporation of CDAS into USGS AROS processing came up in 2016, end of 2015 timeframe, during one of the Landsat science team meetings. And I'll get to why we ended up sort of having confidence in CDAS as one of the good processors for Landsat 8 processing in the next few slides. But overall, the output of CDAS is remote sensor reflectance, RRS, and units of inverse surface radian, as most of the aquatic and ocean color community are familiar with. Because of the terminology and the confusion that land remote sensing folks would have, we ended up essentially adopting aquatic reflectance as a unitless physical quantity, just multiplication of a pi by RRS and get to aquatic reflectance products. And again, it's unitless. The goal was essentially to encourage extensive use of Landsat data for aquatic science and applications, lakes, rivers, coastal waters, and to receive feedback from end users, really, because most of the end users up to last month, the Landsat 8 users at least, they tend to use land surface reflectance products that we do not, as the community, we do not endorse as accurate products for aquatic science and application work. Next, please. Okay, so what's in CDAS, which is unique? One of them is vicarious calibration. So to make sure that we have most accurate products with a minimal bias in aquatic reflectance products, we go through a exercise called vicarious calibration, and that's done using gold standard measurements in the open ocean, off of Lanai in Hawaii, and the current vicarious calibration coefficients within the CDAS toolbox was completed in 2016, early 2016. It has to be updated, but this is one of the aspects of CDAS that we wanted to highlight here. Next, please. Okay, so here's the publication that led us believe that CDAS is a viable approach. Initially, Brian Franz and his colleagues at Ocean Biology Processing Group adopted the L2 gen processing in CDAS for Landsat 8, and the publication came out in 2015. Following to that, this publication came out showing that Landsat 8, in this case, remote sensor reflectance products, are comparing quite well with AirNet OC, AirNet Ocean Color measurements in coastal waters. So this validation is just applicable to coastal areas, and the AirNet data, as most of you may know, providing really a gold standard validation data for the ocean color / aquatic community. So the root mean square differences in inverse radian units you're seeing here, they're very much in compliance with the ocean color community's standard. So this is really, even though the number of matchups are not significant, but it gave us enough confidence to essentially have CDAS implemented in the USGS AROS processing system. Next, please. Here's my last slide. So another publication came out about a year ago. The work was completed in 2018. It was further validation of CDAS processing and its comparison with LeCirc in particular, which is the land surface reflectance processing system built into USGS AROS processing to generate the corresponding products. Again, over coastal waters, and the comparison also with two other atmospheric corrections out there, seeing these results, looking at root mean square errors and biases, we were convinced that at the time CDAS would be a viable option, and that's why we had this discussion with AROS USGS to implement CDAS in the ARRO's processing shop. With that, we can take questions.
Okay, thanks, Nima. As we transition to the Australian Geoscience Data Cube by Stephen Sagard, any quick questions for Nima?
This is Kevin Trippi. I just said one via chat, but I guess I might as well state it out loud. Was vicarious calibration of MOPI and the validation of AeroNet OC done at LLI needed resolution?
Yes, there was a 30-meter resolution.
Okay, and you did like a 3x3 box?
For the vicarious calibration, it was just a 3x3 or 5x5 box, but for the validation, we discarded the center 3x3 pixels to avoid adjacency effects.
Okay, thank you.
Okay, we'll turn it over to Stephen.
Okay, thanks, Steve. Can everyone hear me okay? That's working okay? No worries. Okay, so I think I'm on full screen. So I guess first and foremost, we're part of a federal government program, Commonwealth government here in Australia. Australian Geoscience Data Cube is no more. We're now called DEA, which is Digital Earth Australia. Essentially, it's the same thing. We're an open data cube implementation, and this is the ongoing Commonwealth government program now. The work that I'm presenting here, whilst I'm very much involved from an aquatic perspective and trying to operationalise this, it's really being led by Fu-Chin Lee here at GA and David Jupp at CSIRO as well. So I've got 3 slides. I wanted to go through the background and methodology that we're trying to implement, look at the validation we've done, and then I guess the last slide I think is the one I wanted to focus on. I wanted to raise a few discussion points, things that we've learned, problems we're having, and sort of feed into the broader discussion. So being a data cube, I'm sure most people are aware of the concept. Really the backbone of a data cube approach is to have standardized ARD, consistent, preferably cross-sensor. We have a really mature terrestrial operational workflow. So it's production-based. We can correct to our surface reflectance for Landsat and Sentinel-2. This is a physics-based, so radiative transfer process using ModTran, which does mean it has a dependency on ancillary data. Now that has pros and cons, and particularly from an aquatic perspective, I guess some of the pros are we're not dependent on assumptions about certain water bodies or black pixels we need to find in imagery if we're going to through process for some of our environments in Australia. The cons are multiple as well. Aerosols, we need to have accurate aerosols to have a successful process. This has worked very well for our terrestrial stuff. Australia is very lucky. We have a very low AOD in particular. Whether or not that's going to work for aquatic reflectance is still a process we're working through. We have ASTR observations and climatology post 2012. We source water vapor data and also ozone data. So when we were thinking about moving this to an aquatic ARD, essentially what we wanted to do was stay in that same workflow. So try and just add the additional corrections we thought were required. So we have surface corrections, we have a diffuse skylink correction, a sunglink correction, which I've put optional in, and I'll explain a bit more later why I've put that as one of the discussion points. We have an adjacency correction, which is based around the point spread function, which we've now got incorporated into ModTran, and we've added the ability to switch between ModTran aerosol models. So we've done some validation. Last year we had a coastal validation. We've got one AeroNet site. Nima's described the AeroNet data. I guess we use Lucinda Jetty up in Queensland. It's quite a complex water site, coastal site, changes quickly over time. And we also had a couple of survey points from a Northern Australia survey we had. Ended up with 20 Landsat 8 Ollie matchups. We had Thomas Schroeder from CSIRO do the work for us on this in terms of a somewhat independent matchup. And Nima was actually good enough to supply us with some comparative CDAS, I guess what the aquatic product is now for them. So we could sort of do some baseline against that. And also discussions with Nima sort of shed some light on the benefits of using top of atmosphere reflectance for our Landsat processing, which we hadn't been doing previously. So the 3 scatter plots there on the left is our processing with everything apart from the sun glint correction. Obviously you can see outliers there. Then once we implement the glint correction, very much on par with what you're getting from the NASA, from the L2Gen or the CDAS data. And down the bottom there, you can see I've got a couple of the instances, one extreme example of glint, where you can see the cluster of different processing variants we have before we apply the glint correction. And then here we've just got an image where obviously there's less glint influence. We hadn't really done any inland water validation, primarily for the fact that we had no in situ matchup data in Australia, or very sparse. We did have a field campaign slated for this summer, working with CSIRO as part of our inland water project. That was really hijacked by the bushfire season in Australia. So we couldn't get out for many of the matchups we planned. We did manage to get one towards the end of February or mid-February. This was at the tail end of the bushfire season, which also has some interesting repercussions that we'll discuss in the next slide. So I literally did this week, do a bit of a match-up, thinking that if we're going to do a Geo AquaWatch talk, that we'd need something for inland water. So this is the two sites we have. This is a Sentinel-2 processed image. We get a reasonable match-up across the visible bands. We also got a chance now to sort of evaluate whether the adjacency corrections doing what we expected to do. Very hard to validate quantifiably. So we can look at, you can see up here at the top right, we've got the blue, which is our standard terrestrial reflectance data, and you can see as you get closer to the bright coastline of the lake, which is a sandy sort of coast, that you get the expected response from the adjacency correction. So I guess the discussion points that I wanted to sort of leave with everyone, and hopefully this is the kind of things that we've been thinking about. The first one is, I guess, what level of processing is appropriate for this operational ARD? And I use the glint as an example because what we're using in the glint correction is really a global surface roughness, so Cox-Monk's the standard process for ocean color. And we've noticed, and we've seen it, I think it's widely accepted, that this can create anomalies, negative reflectances, if we don't have an accurate wind speed, or there's localized wind or surface roughness, and even in high resolution data, so Sentinel-2 particularly, pixel-based glint isn't really dealt with effectively anyway. I guess the overarching question is, do we want to force this on end users if it's a process that can't be undone? Obviously it's needed. We saw that in the validation slide. So we've provided as an optional module on top of the processing. Similar to the way we've sort of thought about our cloud masking in the past, is that previously when we've worked with Sentinel-2, the cloud masks haven't been sufficiently accurate, so we considered buffering. But this is a process that loses data, particularly from a time series perspective, and you can lose good data. So do we want to force this on people? Secondly, our ancillary data dependency is something that is important. If we deviate from the climatology, we can't account from that. The Sentinel-2 image that I showed on the previous one, we're pretty sure that this is affected by the Australian bushfires, that there's a much higher AOD than what the climatology is reflecting. And it means that in our operational workflow, we can't really account for that. And it also means, because we've got an Australian climatology, that it's hard to transfer this workflow internationally, which has impacts to our participation in international initiatives. And we're still sort of working through where we play in this field, whether or not we can use our findings to sort of help influence international efforts, or where we play with that. We have had some luck using a motor-based AOD for coastal work, but again, that's Australian-based. Next point, which is news to no one probably on this call, that validation is difficult at scale. We had nothing for inland waters, and what we do have, even for coastal, various protocols are often used, so it's very hard for comparisons, and getting match-up data is tough, full stop. And something important from our perspective is storage and delivery. So considering this for Digital Earth Australia or an open data queue, where essentially you present the data, people come to the data, so you need to store that data somewhere and supply it. This will mean another full continental collection effectively of Landsat 8 and Sentinel-2 level 2 data. So it has implications for our storage costs, whether we're on a hard disk, whether we're on a cloud compute. And this is all at the same time when there's a bunch of competing data sets in that space, Sentinel-3, those kind of things. So whether it's feasible to do this kind of thing on the fly, which we suspect very much not, it's an implication for what we actually do, and convincing programs which are land-based that they need another 2 collections for aquatic data is also a challenge. So with that, I guess I'll wrap up, and hopefully those questions are something that we can bounce around. Cheers, guys.
Thanks, Stephen. Those are good points to ponder here. Any quick questions for Stephen as we transition to the ESA Sentinel-2 by Karsten?
Stephen, this is Brian Kill. Just a quick question for you. You're still processing all of this on the Australian supercomputer, right? None of this is in the cloud yet?
No, that's right. It's all still in the NCI and not yet on the cloud. And I guess we're going through that analysis process around cost of processing versus cost of storage, etc., on AWS for all of our products at the moment.
I was getting at your very last point, is this something that could potentially be done on the fly if it was done in a cloud with, some of the cloud computing efficiencies are quite high now, and you can do a lot on the fly.
Sure, I think our process needs a bit of tweaking in terms of the computational load. The point spread function particularly is something we've found is really computationally intensive, but possibly yes.
Stephen, this is Ajit, and I had a question about how you were thinking about that glint module that you have as an optional. Do you have flags or something like that you might alert a user to the fact that this is something they should think about?
Yeah, that's definitely one way we went down is part of the glint process essentially does do a flagging based on geometry and surface roughness. And so whether we can provide the capability to either correct the glint using that method and user beware, or we can provide a flagging type system around high potential glint areas and things like that, especially when it's systematic looking out, especially for us on the Great Barrier Reef and on the eastern seaboard looking out towards the east, it's quite systematic. So yeah, for sure.
Right. So that's almost exactly what I was thinking about. I was also curious to know how your processing deals with surface cyanobacterial blooms, such as the trickle blooms that happen around the Barrier Reef region.
In terms of it being more of in terms of the influence on the reflectance signal and the assumptions made therein?
Yep.
So we don't need to make any assumptions, I guess, around the reflectance of the water body for this. It's somewhat agnostic around that. Apart from the fact, I guess, talking about the variations in surface effects, but in terms of needing to, with some algorithms, I guess you need to think about a minimal reflectance in the near infrared or shortwave infrared. That's not really an assumption we need to make. So I would say that the effect is minimal. We haven't, not that we're testing this.
Okay, I think we're going to move on. Thank you, Stephen. Karsten?
No worries.
We can't hear you if you're talking, Karsten.
No, I was talking into nothing. Okay. All right. I think you can see my screen already.
Yes.
Okay, good. So I took the liberty to add Sentinel-3 to the Sentinel-2, what you asked me to talk about, because I think it makes sense in this context. And so to start with, I was reading the paper and I had some thoughts about it, and I will not go deeply into it, but analysis ready data is really important to think about what is the analysis which is done, because this tells us what are the requirements for the readiness. If we want to have this long list of detailed requirements for aquatic reflectances, we have to understand what is the analysis to be done, and then we can say what do we need for ARD. So at the bottom line here, I have put here what is basically the level 0, level 1 measurements by the sensor in space, and then we have the first step to get the radiometric measurements at the water surface. And then comes an analysis which gives us the water quality parameters, so IOPs or concentrations. And then comes another analysis which gives us, maybe in a time series, the time step where we have the status of the water body with its history, and it allows us to do prediction. So what we're talking about here, I believe, is that we go from the water quality parameters as the result of the analysis, and this gives us the requirements for the ARD. And we don't have time tonight, today, but I believe when we talk in detail, for example, normalization, not normalization, we have to keep in mind that the analysis is we want to derive good water quality parameters. Just to mention this, but also in the paper, when we have on the application side as the result of the analysis, monitoring activities, climate science, marine spatial planning, If this is the result of the analysis, then we have the requirements on the water quality parameters, and this is what is called IRD interpretation ready data. Okay, so having said this, we have here also a little bit of analysis of what level of processing can we apply, and what is the price to pay if it's more easy to use. This is also the idea of ARD. We probably increase uncertainty or error. We reduce accuracy in the data. If we stay in the variable space, we're talking about reflectances. We have good metadata. We can normalize on the methods, on the masking and everything, but basically leave everything in its original coordinates, the time stepping, and we would be here. If we apply a common grid to it, then we map, and we may apply nearest neighbor or big cubic, and this increases the uncertainty. Next level of making it more easy is to put everything in regular data cubes, and we can either preserve the original times or even interpolate in time. And this makes it more easy for user to access it. However, there is a price to pay. At least for this step, we increase the uncertainty. So with Sentinel-3 Algae, and actually Merisforce reprocessing is more or less at the same level as Sentinel-3 Algae, we stay here. We are very close to the original satellite data, because for aquatic applications, to derive good IOPs, good concentrations, uncertainty should be minimized. With Sentinel-2, we are in this area here, they are mapped already at the level 1C and come on a regular UTM grid. And then we have, in Europe, we have further levels of processing, for example, in the Copernicus services, or what ESA is currently doing in the Eurodata Cube, where we go this step. And this is also what I touched upon in my last slide. So as I said, Sentinel-3, which is really an ocean color sensor, which is also with the 300 meter to the larger lakes, and Merisforce reprocessing, we are in the domain, in the typical domain of the watercolor sensors. So with Sentinel-3, what we provide there, or what ESA is providing there as standard products, I don't want to call it ARD a priori, is a product and per pixel metadata, which are quite complete when I compare it with the CARD4L requirements already. The product of interest here is the water leaving directional reflectance. I put here directional because in the paper it was said should be normalized, with the OC4ME atmospheric correction. And quite interestingly, it provides uncertainties on the rho W, which is calculated in a certain way, I think, which is also kind of requirement. Quality annotation per pixel comes that we provide AOT and angstrom coefficient, pixel classification information if it's clouds, intertidal, and some other qualification, and then some flags which arise during processing if there is whitecaps, glint, details on the atmospheric correction, or finally if the atmospheric correction failed. So that's quality information. The georeferencing, as I said already in my previous slide, we stay in satellite coordinates, so no remapping to a standard grid. And Merisforce reprocessing, just to mention, this is called Algae-like, so we have basically the same variables where possible, same definition and algorithms, and the same product format. It's not the same, it's called Algae-like, so there is differences because it's different sensors, and the full archive is reprocessed. Because the normalization, I talked about it, there is an external tool made available through UMITSAT, which is applying a BRDF correction to the directional reflectances. Because if you would apply it in the product, it cannot be reversed. So that's why it's an external tool. This is just that we can look at one image today. If we go here, you can see the spectrum, you can see the uncertainty or the error derived with it. And this is just a part of the metadata which comes with it on the product itself. And then here is on the processing, the name of the processor, version number, where it was processed, and so on. So it's metadata is quite important. Sentinel-2, the product of interest here is the level 2A product, surface reflectances. Looking into the metadata, I haven't checked it as detailed as for the other ones, but I guess it's more or less complete with the Card4L requirements, because I know that Ferran and colleagues are quite close to Card4L. I haven't looked into the metadata per pixel. The reflectances it's a land atmospheric correction, and as said before, this doesn't meet the requirements for atmospheric correction, and I come to this next slide. And in SX2, Nima will talk about it, several water atmospheric corrections for Sentinel-2 are compared. Quality information, AOT is provided, scene classification layer provides cloud mask and others, but not really covering important water features like glint, lake, or sea ice, floating vegetation, and so on. So it's really necessary to have a dedicated water product from the ground segment. Georeferencing, as I said, it comes on a UTM WGS84 projection and the MDRS grid. I think it's the same as Landsat. Just to mention this, that ESA is undertaking what is called a Send-to-Like processing and combining Sentinel-2 and Landsat 8 with the objective to create a tile-based, multi-temporal, seamless surface reflectance product, but also this is using a land atmosphere correction. So in the Copernicus services, there are dedicated water products. And as I said, the Copernicus services provide basically level 3, level 4 data, so temporal, spatial, integrated products. That's what I put here. The marine service is currently providing ALGI level 3 product. These are daily composites, remote sensing reflectance, and then also water products. And it has a level 4 product, which is a gap-filled monthly averages. And currently in preparation is a coastal product from Sentinel-2, and operational distribution will start in January 21. This is an open tender, so I can't tell you who will win it and what will be the atmospheric correction to be applied there, because it will probably not start from the level 2A. On the inland waters, we are one step further. There is as part of the Copernicus land monitoring service, since some years already, an inland water service. This is using the columnus processing chain, which for Sentinel-3, ALGI is using polymer as the atmospheric correction. It comes as 10-day composites with a water leaving reflectance and an algorithm which is a best spectrum selection, so not averaging on reflectances, and the water products are averages. Sentinel-2 demonstration products are also available and ready for evaluation by the community. And on my next slide, I show you what is also done in the Copernicus land monitoring service as a way to process and distribute large amount of data. As Stephen was already saying, it is an issue when you come to Sentinel-2. Oh, sorry, this is just a snapshot of the coastal ARD. I skip it. So this is the Sentinel-2 global mosaic. It's an on-demand service. So the whole globe is available to users, but processes only what is requested. So the time frame, the area can be selected, the details of the product can be selected by the user, and then the product is processed for him on demand. This is an annual 10-day composite product from Sentinel-2 as one example. As I said, this is currently with the land atmospheric correction, and so it's not at that level for the marine side yet. And last point is when we come to bringing this all in the time and space regular grids, there is the initiative of European Space Agency on the Euro Data Cube. They call it the O Information Factory, where one of the objectives is to support distribution of analysis-ready data. So that's something which is just coming up now. And this will build on the data to be processed by the ground segment. So for land, it's on a much better situation as it is for water. It's a great opportunity for this community to give the right recommendations for what should be done for water. All right, that's it.
Okay, thanks, Karsten. It sounds like this is a timely discussion. So as we transition to the GRIS talk, any quick questions for Karsten?
There's something in the chat. from Dan Woodrow.
Okay, maybe we'll hold that for the discussion. Let's continue with Ed's talk here.
Okay, good afternoon, everybody. It's Ed Armstrong, and just wanted to make a brief introduction. I don't recognize many of the names on the telecon. I'm kind of new to the CIOS community. I've been the co-lead of the SST virtual constellation for about 6 months and attended my first SIT meeting. But I work in the NASA JPL PODAC. I'm an information technologist, and for more than 20 years, I've also been involved with the Group for High Resolution Sea Surface Temperature project. That group that seeks to standardize, not only working on accuracy and cloud masking issue on sea surface temperature data sets at the international level, but also standardizing those products with standard data models and metadata models. So I wanted to talk a little briefly today about the analysis ready proposals that we're working on in the virtual constellation. And of course, this is also closely coupled with the GRIS project and GRIS data sets. And so from the perspective of ARD formulation, I think my talk is going to reiterate on a lot of the themes that have already been presented here. But really in my mind, when people talk about ARD, there's really two separate topics in that theme. And the first one is the data structures and the commensurate interoperability that are necessary to construct an ARD. And then the second one is the data storage component, where once the ARD has been created, where it's stored and how it's accessed. And so most of what I'll be talking about will be on the first point, but I will show you an example of the second point in my last set of slides here. So with regards to the data structures and interoperability, it's really about conformance to Earth Science data interoperability standards as a foundational element, including things like having things in self-describing formats at the granular level, having proper metadata standards such as CF, ACDD, and ISO, as well as implementing community vocabularies to describe things like variable names, and that can include things like CF standard names. And so on the data storage end, when we think about ARD, we often think about commensurately with cloud. Of course, there are cloud optimized formats, such as ZAR, cloud optimized GeoTIFF, and as well, and with that, then also is the data processing ecosystems that these then ARDs are operated on, including things like Pangeo, and that's tightly coupled with things like the Binder Jupyter framework. And as we've seen then, in the ARD definition often depends really on the community that you're talking to. It depends on the processing level. It depends on storage and access methodology. And overall on the Earth Science application and community. So, the ARD definition, I think, is different for level 1, level 2, where it's a little more complex than at the higher levels, like level 3 and level 4. And I'll show you an example of what we've done on the level 4 with regards to an ARD that's available right now. So what we want to do within the SST virtualization constellation is, what we're proposing to do is to really review and summarize the state of ARD across the different virtual constellations. We want to first focus on the SST and the Ocean Color virtual constellation, but what we really want to do is applicable across the board, and focusing then on the data formats and metadata structures. So those foundational components that you really need to know and get right before you construct an ARD. That includes things like the variables and the services that are on top of those variables, as well as understanding things like uncertainty measurements, quality variables, and transformation capabilities. So, across the spectrum of the VCs, starting first with the SST and OC VCs, what is the state of the current data sets? How amendable are they to transforming them into an ARD format? And so we want to identify some of these gaps and potential future improvements with regards to interoperability, across these interdisciplinary VC products. And so again, in the first year, focusing on the SST and Ocean Color VC, and then looking at the other ocean VCs, including wind and sea surface height later on. We also want to look at things like ARD storage and cloud optimization and data recipes if we have time. And we've been kind of trying to like closely align our work with the needs of the CIOS Coast activities to see, how well, we want to basically make some positive impact to the tools and services component of what they're working on and support their project implementation. As well as we want to engage. We realize there have been, existing ARD efforts that we heard earlier in some of the earlier presentations, and we definitely want to partner and hopefully our work can be of value to those efforts as well. So that about wraps up what we plan to do in ARD in the next 12 months. But I wanted to just kind of briefly show you one success story here of a cloud-based Amazon data set. This is a GRIST mirror data set that was refactored and transformed into ZAR format. Now, Mirror is a very popular GRIST level 4 SSD data set. It merges both infrared and passive microwave SSD measurements on a global 1 kilometer scale daily. So there's a daily product created every day, and it has, a few hundred unique users every month. So it's a pretty popular data sets that's served from the GRIST archives. And this activity was led by Gel Gentleman. I just had a very modest role in it, but she's part of this NASA Impact program, and her team refactored and transformed this mirror data set into a ZAR format. And it's part of the Amazon Web Service Open Data Registry now. And there's actually a GitHub site where you can download some software. This is the Pangeo ecosystem that I described. That provides the complete ecosystems, including things like Jupyter and Binder, working on top of X-Ray and DAS to manipulate this ZAR data set. And you can, the beauty of the cloud is that you can scale from just a few or to 100 CPUs as you need to make easy or complex calculations. Again, this is supported by the NASA Impact program. And so if you go to that URL right there, you can download this software, and there's some examples of creating climatologies and doing anomaly analysis. But really, the framework that's presented there amends itself to doing other much more complex calculations, such as EOF analysis or things that require much more CPU intensive. So I just wanted to present that as a small success story. I realize that level 4 is probably one of the easiest data sets to kind of tackle and roll into ARD, because there's not it's already usually a single variable. There's not too much analysis, variable or information that the user would need to access to be able to work with the data. It's really good out of the box. But it shows at least one roadmap in oceanography how an ARD was constructed, and with a complete software ecosystem that allows users just to start working with the data right away. And I think I'll stop right there. Thank you.
Okay, thank you. Any quick questions as we transition to Nima to give us a little brief update on ASICs? Hearing none, we'll move on. Okay. Go ahead,
Okay.
Nima.
Sure. Sorry for the delay. You have to hear me out again. So ASICS Aqua. ASICS stands for Atmospheric Correction Intercomparison Exercise. This was co-led by myself and Antoine Manger with ICRIST. The whole exercise, the first phase of the exercise, started in 2016 or end of 2015. The first one, this one included only land. It primarily focused on atmospheric correction methods and processors focusing on land and validating over land, would see it as an acolyte being part of it to look at coastal waters. But ASICS Aqua is primarily focused on looking at atmospheric correction processors and the performances over freshwater and coastal ecosystems. The objective, we wanted to lay the groundwork for global production of aquatic science products from Landsat OLI and Sentinel-2 MSI. More specifically, looking at identifying strength and weaknesses of atmospheric correction processors. We wanted to inform users and agencies of the performances of different atmospheric correction processors, and we wanted to also assess impacts on downstream products, primarily focusing on chlorophyll A and total suspended solids as TSS. Also wanted to, as a byproduct of this activity, we wanted to quantify the uncertainty requirements for aquatic reflectance products. So ASICs, we started off with 8 different, we started off with 12 different atmospheric correction processors. 8 of them happened to be sticking to us. We had a data team who provided field radiometric matchups under Landsat 8 and Sentinel-2 overpasses. We split the data into 2 parts, into phase 1 as ARNet data or ARNet OC data, representing nearshore coastal waters, and phase 2, which included data from the data team over freshwater ecosystems. Initially, we had about 4,000 matchups. End of the day, as you would expect, we ended up with about just over 1,000 good data, good matchups to be able to use for validating and intercomparisons of these processors. The initial results were presented December of last year, and now we're working on compiling the results and ready for submission for peer review. Here are the folks who contributed to this effort, 15 individuals and teams from 15 different institutions. Processing team included 8 individuals who were point of contacts for the AC processors, and there were support at AquaWatchARDC and NASA Goddard Space Flight Center, where I work. Okay, so I have a lot of slides to show, but I'll just squeeze everything down to few slides. So everything is presented separately for freshwater and ARNet OC, or coastal waters, if you will, because the ARNet OC, as I mentioned in the previous presentation, it provides gold standard validation data. So we know what the uncertainties are associated with the measurements. And the freshwater, they're coming from all over the place, mostly with, not mostly, all of them were collected with hyperspectral devices, spectrometers. So here are 8 different processors for freshwater and 7 different processors for coastal waters to the right. ICOR was the only processor just wanted to essentially be part of the freshwater analysis, so it wasn't applicable to the coastal areas. What I'm showing here is the error values. The error simply corresponds to median uncertainties. So it's a median, it's picked as median just because we wanted to avoid any outliers in our institute data set. I have set a bar here, it's a 20% threshold, and it's just an arbitrary uncertainty for this median error expressed in percentages. So if you can see, for the 4 different channels of OLI and MSIs, we're just looking at the visible bands here for now. The performance of only 2 processors meeting a 20% sort of uncertainty requirement, if you will, and those are in the green and the red channel. The rest of them are just above 20% in the green and red, and in the blue bands, things are much worse, as you might expect. And on the other hand, for the coastal waters, we're looking at much lower errors. Most of the, couple of different processors, including CDAS, Polymer, OC Smart, Meet C2, are sort of meeting that 20% threshold for only one channel, a green channel. And the red band, you're looking at 30%-ish error and uncertainties. So overall, you see that the performance are overall better over in coastal waters, and that's kind of expected. By the way, we're throwing out any suspicious data. That includes even looking at glint affected pixels. We're excluding adjacency effect here. We're just essentially using clean data, if you will, for this analysis. So you may wonder about MSIs, near infrared bands, 705, 740 nanometer, 783. Here are the uncertainties. Again, same thing, same story, median error. And we put it like 30% threshold here, just allowing sort of relaxing the threshold, knowing the uncertainties in the instrument in these spectral region. You see like Acolyte is meeting at that kind of 30% threshold, and the rest are quite not, but they're almost there. But the uncertainties are much higher than 740 and 783 nanometer, except in CDAS and iCore. One thing to mention, this is not really an apple-to-apple comparison, including this slide and this slide, because we're using different numbers of, we're looking at different numbers of matchups for each processor, because they're not using the same thresholding sort of scheme in their processing. So that's one thing to keep in mind. It could be done with common set of matchups as well. So I showed you basically maybe 1 or 2, 3 processors meeting the 20 to 30% threshold in aquatic reflectances, but really what that means, what does it mean to the products, to the end users? So what I'm presenting, what I'll be presenting to you is looking at the impacts of these error values on chlorophyll A and total suspended solids. So 2 possible approaches. That's basically number 1, use common matchups, about only 140 matchups among all the AC processors for a universal uncertainty quantification. What I showed you in the previous 2 slides were roughly on average about 400 to 500 matchups for all of the processors. So if you want to look at common matchups with TSS and chlorophyll available, we're looking at about just 140 matchups. The second approach is basically use field data to do field radiometric data to derive chlorophyll and TSS and use those as a validation, the truth in code, quote unquote. So what I'm showing to you in this slide is basically on the x-axis, the field-based radiometric retrieval. You have the near perfect, quote unquote, retrievals from radiometric data in situ, and then you compare it with the satellite retrievals on the left, on the y-axis. So we're looking at OLI-derived chlorophyll A over fresh water only, and we're basically using only 4 visible bands, and we're combining MSI and OLI data to do this analysis. So as you can see here, the top rows corresponds to the a newly published chlorophyll A retrieval algorithm called a mixture density network, or MDN, and the bottom plot is looking at ocean color X, or OCX, the blue-green band ratio used for this analysis. So as you can see, the different atmospheric corrections have different sensitivities to their uncertainties in the atmospheric correction and aquatic reflectance products. So this is sort of enlightening us in terms of what a processor should be used with what type of algorithm. And the errors, roughly, I have tables and quantification and numbers for you, but as it's indicated here, the errors in chlorophyll retrievals and chlorophyll estimations are about 60% at best case, okay? That's a takeaway from that slide. So for MSI, where we have the near-infrared bands, we know we can do better for chlorophyll A retrieval, especially in eutrophic systems. Here are the same thing in the vertical direction and same X and Y axis, but looking at multiple different chlorophyll A retrieval methods, MDN, just got published recently, blend, Gillerson 2-band, etc., GONS, same story. The chlorophyll A, uncertainty in the chlorophyll A that we're achieving is about 60%, maybe 50%, again, depending on the number of matchups you're using for the analysis. As you can see here, all the numbers are different here just because the algorithms are always not functioning, just because they're sensitive to a range of chlorophyll A, except MDN and blend here because they're applicable for the entire range of chlorophyll A. And if you look at numbers, we're looking at 0.5 milligram per cubic meter all the way to 100. So it's a decent range of chlorophyll A. Let's look at TSS, only using visible bands, same story, X and Y axis. 2 methods we're analyzing, Nishad et al. 2010 and SOLID. SOLID is a new approach that will be published in a week or 2. What's striking here is how SOLID is sensitive to the atmospheric corrections for across the board. It's a machine learning based algorithm and the backbone, and that's interesting. On the other hand, if you look at Nishad's performance, for most of the processors, it seems to be resistant against the noise in the atmospheric pressure. That's an interesting observation across 8 different processors. So there is a lot to talk about in terms of recommendation that should be coming out of this work. I'm drafting a paper. Everyone has to comment on it, so I can't give you all the recommendations. But one thing that I kind of highlighted here is that at global scale, with 20 to 30% uncertainty in the visible near-infrared bands, excluding the 443 channel, about 60 to 70% uncertainty in chlorophyll A and TSS is possible over freshwater and coastal waters. This could slightly change, and as I said, it's going to be another month or so for this, to the submission of the work for peer review. But within the next couple of months, I'll be reaching out to some of you folks for comments and feedback on this effort. With that, I'll pass it back to Mary Beth and Steve.
Okay, thanks, Nima. This is quite revealing and insightful. And as we've talked, the atmospheric correction plays a large role in this, the analysis ready data portion. So I don't know if we have time for a question. I just wanted to point out that we're well after the hour, and I think we're just going to continue on here and power ahead. At this point, I'm going to bring in Arnold and Rob Woodcock to talk a little bit about some of the issues and again, kind of prime the discussion moving forward. So with that, Arnold, are you going to?
Yes, I'll kick this one off. I'm going to do it very, very shortly because I think we should go to the open discussion almost immediately. How do we get here? Within AquaWatch, within the team that is leading AquaWatch, about 2 years ago, we began to realize that we have a problem, possibly a problem with end user trust. If we have different algorithms, poor validation, and on top of that, different ARD providers with different methodologies, it is likely that at a certain moment, in areas on the world where different ARD providers with different algorithms provide products to the same end user, the end user will get very confused if those products do not align, for instance, chlorophyll or total suspended matter. So this is an important issue. We must make sure, and I think that's what AquaWatch wants to achieve, is trust. And because of that, we reached out to CEOS WGIS, and you've seen several of the results of that in the earlier talks today. So we are thinking about the end user. And the other point we have to think about is, currently we're discussing inland waters and coastal waters and ocean waters separately, but there should be ultimately a seamless transition between inland to coastal to ocean waters, because in the Amazon and in the North Sea and in the Yellow Sea and on the Great Barrier Reef, we have massive amounts of fresh water flowing into oceans. And at a certain moment, we're going to have to deal with that as well globally. So those are two aspects I just wanted to mention. I think the speakers have already given so many examples and ideas and problem points that I think we should go straight into the discussion from here.
Okay, thanks, Arnold.
So, Andrew Tyler.
Sure, I appreciate that. And as Arnold alluded to, we've thrown a lot at you here today in the last hour or so, and we're going to enter into the discussion. And I'm going to have Andrew turn over the reins to Andrew here to lead this discussion. Andrew, are you there?
I'm here, Steve. Yes. Good evening, everyone, or good afternoon, good morning, as appropriate. Thanks very much for those presentations. It's been really, really useful just to bring us up to date in terms of state of the art for potentially for ARD. Perhaps whilst we're thinking about this, I could just have one or two reflections, if you excuse the pun, on this thought. I think ARD presents a really exciting opportunity. Arnold clearly identified the potential conflicts that we have if we're all producing global data sets and yet they don't agree within countries, within particular lakes. But certainly from my conversations with a number of potential partners that are really interested in taking up this capability, particularly in developing countries, they really want to be able to do this themselves. And if they can access ARD data, that takes out a lot of that heavy lifting in terms of data processing for them. And they can then obviously apply their own algorithms. And that also then helps build the trust because they develop and use the data themselves. I think that's something we do need to bear in mind. So I think the discussion should really confine ourselves to producing ARD data in terms of remote sensing reflectance or radiance. For I don't know how long we have for a discussion at this moment in time, but so that's my first reflection. I think there's a real opportunity there. Perhaps just to kick off, we could ask a quick question, and in terms of just looking at those presentations, are we ready? Is perhaps one question we should ask ourselves. Are we ready to do this at the global scale? And if we're not, what does it take to be ready? Can I maybe start with that, particularly on reflections of some of the NEMA's uncertainties on atmospheric corrections?
Nima, would you like to respond?
Oh, so I was wondering if that was.
You didn't have to, Nima, but that was a general question to everyone.
Yeah.
Oh, okay. So I'll let everybody. I have enough time.
My opinion. I think we need to start, and now's a good time to start. But I just think we need to get that confidence up as well.
Sure. So I think everybody almost mentioned that it depends who we are targeting. With some of the experiences working with other countries, especially in South America and Africa, needing to monitor their water resources and really wanting to use satellite data for their monitoring efforts. I think we're almost there, and there could be some different version of ARD, but they have to be provided to these countries in need, given the uncertainties, because the monitoring is of course, the needs and requirements are different from science needs. So from what we're seeing in this atmospheric correction into comparison exercise, I think we're there in terms of monitoring. There are a lot of complexities, but we have to start from somewhere. Implementing CDAS and USGS AROS processing. We knew that CDAS is not perfect, but you have to start from somewhere.
This is Brian Killow. I just wanted to throw in a few thoughts here about the question there, are we ready? I don't think we want to get tied up in the question about which correction algorithm is the best at this point. NEMA obviously showed several of them out there. When you talk about these ARD specifications, it's more about the requirements for how the metadata should be put together, what are the geographic correction methods and accuracy, what spectral band information, radiometric accuracy. It's more about documenting the process by which the product is created so that a user understands it from beginning to end and can possibly reproduce it on their own. And it's less about the choices made precisely on, the detailed knobs that are turned to create one product versus another. So for instance, I'll use the example for surface reflectance for Landsat data. It is possible that someone may do their own surface reflectance product for Landsat data, and it could differ from Landsat's created product, but both of them could meet the ARD specifications. It's just that they go about it in a different way. They might have a different end data format, or perhaps their accuracy threshold is not exactly the same as Landsat's. So I'm just throwing that out there that in a way, I do think we're ready to pursue this if the community is willing to think about what are the overarching requirements necessary to guide the selection of this processing process.
Yeah, that's very helpful. We talked, and Arnold talked about trust, and I think that's a really important point as well. How do we do that? How do we build the trust? Do we want to have a set of approaches that we would, if you like, almost quality assure, or give some kind of standard of quality to, so that we know that if people are adhering to those, then they could carry that badge of quality, if you like. I think if we have this ARD approach, whichever way we take it, it also helps avoid, or it goes a step towards people misusing data as well. I think we've seen a few cases recently where data is being processed inappropriately and publicized as well. For example, around the Venice Lagoon and so on, which has been completely incorrect. So I think we do this, which I think we should be doing, but there should be a quality component to it and a standardization approach to it as well, so that we can build a mark of quality and confidence in the community.
Yeah, that's exactly what the requirements have. If you look at the ARD specification for, for the surface reflectance products for land, there are threshold and target requirements. And really deep in the detail, if you're not worried about metadata, those are kind of really simplistic. But if you look at some of the details regarding georectification or radiometric accuracy, that really does get at the quality of the data. And so when it comes to things like aquatic ARD, there's likely going to be a tighter specification for how that atmospheric correction is done. And perhaps some of the other things like Stephen had mentioned, maybe a target requirement is to correct for the, the surface, some of the surface perturbations and issues, whereas that might be less of a problem for land and might never really show up in the land correction, but for water surface it might. So it's those kind of subtleties I think really do get down to the quality of the product.
If I may enter here and point to Nima's presentation and the second part that you showed, the impact of the different atmospheric correction on the water products. This was really interesting, because what matters at the end is not really the accuracy of the water leaving reflectance. What matters is the accuracy of the product, and the sensitivity of the product to the different atmospheric corrections was depending quite a lot on the algorithm, as you showed, which is not new, but it was very nice to present it in such a way and to have done this analysis. And this makes me really think, if we are really there, that we can say we are ready to produce ARD data. I think there are so many questions on the table. I agree that we have reached a good status with, we have reached a certain status with atmospheric corrections for coastal waters. That's good. For inland waters, it's still a lot of work to do, but maybe we can go ahead, and I mean, we do. However, if we think of ARD and then asking the question, ARD for what purpose? What is the analysis to be done? And then looking at your second part, I think it needs another round of thinking.
Thank you, Carsten. That's very helpful. Did anyone else want to add to that?
I'll just point out there are several comments in the chat.
So maybe if we go to some of the questions. So Dan, you posed a very relevant question at the start. So we'll, before we got to this discussion, Dan, do you want to pick up on your question?
Yeah, sure. So I work for Frontier SI. So Dan, I'm in Australia, and I've come from, although Earth observation is where I started many years ago. I've come from a bit different area, so I've recently been working with, for example, an agency that's been formed to manage the coastal environment. Essentially, it's a mixture of state, local, different levels of government, industry, developers, everything, because in somewhere like Australia, and this is probably the same in many places around the world, that's where the focus is, the coastal areas. There's a lot of activity there, as concentration of human activity, and a lot of pressure on resources. So they've got this, just as an illustration of what they want to use stuff for. I did a recent study, and there were about 100 data sets that they identified that they used in the marine estate, as they call it here, management process. So, and these range for everything from sort of just great aerial photography type imagery for context to quite specific things like thermal discharges, vegetation mapping, water quality, algal blooms, a whole range and raft of stuff, which quite a lot of which is potentially, fertile area for I guess a derived EO product that you've been talking about. They just, the language that people use and what that comment on metadata, I think, was really important, because people just, the problem is that there's probably only about 20 of those that they've actually identified as having a source for. So there's a real problem in data availability. You might have an out of date source, or something that's very old, or something that's inconsistent in its geographic coverage or approach. So there's a real need for consistent and broad scale, relevant scale, but broad coverage, repeatable, all the stuff that EO is, as we know, in many cases. But there's a real lack of it, and a lack of understanding of what's available. So when you talk about, the people I've been talking to wouldn't have a clue what you guys were talking about today. They really wouldn't. I'm not being really rude. I just mean that a lot of they would just think, wow, that's a science that's not applicable to me. I need to know where the oyster farms are.
That's a very good point. We have within AquaWatch, we have undertaken a global questionnaire, which we tried to complete last year. We're still doing the analysis of the data on that, just to assess, well, basically community understanding of what potentially Earth observation can provide. And I have to say the responses are very mixed, because I think, obviously we know what the potential is, but actually the message really isn't out there yet within the user community. I think the potential is enormous, but there's a lot of work to be done. And again, there's a sort of capacity building outreach component to AquaWatch. There is a lot of work still to be done in that aspect. Our experience also is working with users is that it's very important that we also co-develop the products with them, so that the data is of use to them in an appropriate formats as well, once they get to understand what the potential is. But there is a lot of work to be done there. I'd agree with you. And a common language, or an accessible language, is also very, very appropriate.
So, Andrew, there's some questions in the chat. I don't know if you want to go through them.
So where did we get to? So John Scales, do you want to pick up on that one? Are you still there, John?
Oh, yeah, I'm with you. Thanks, Andrew.
Hello, John.
Nothing earth-shattering, but we've known for some time that Landsat, for instance, just doesn't have the bands that would be optimal for water quality. Yet it's surprising to me in recent years how much is possible with that. And obviously, it's always in the future we're going to have more bands. I know that Arnold, when we had the GeoAquaWatch workshop in Stirling 2 years ago, had advanced a feasibility study for a CO study, Earth observing systems that optimize. If we could have the optimal set of bands, what would they be for water? Arnold, is there progress on that?
Hi, John. Yes, so the SEALS 2018 report is on the SEALS website for an aquatic ecosystem Earth observing system. Essentially, it's recommending imaging spectrometry if you look carefully, or I think at least 43 multispectral bands, which is similar to imaging spectrometry. There are developments. We've got Prisma from the Italian Space Agency is now in space, so you can order data from Prisma if you're a researcher. DSIS is on the International Space Station. You can get data from that imaging spectrometer through German aerospace laboratories if you're a researcher. Otherwise, you have to pay commercial tariffs. Hisui will be available, the Japanese imaging spectrometer. But none of them were developed for inland or coastal waters. They were generic imaging spectrometers. So currently in Australia, we've got a program to do a phase 0 or phase AB study on actually implementing the SEALS recommendations for an aquatic ecosystem imaging spectrometer. But there are also in Canada, there's lots of developments with possible satellite imaging spectrometers for water quality, and ESA has a new call for sensors for, I think, for Sentinel-11 from memory. It could be a different system, but ESA is going to come out with a call for sensors. So I think there's quite a lot of activity in this area. But we don't yet have a dedicated aquatic ecosystem imaging spectrometer in space, but I think we're getting closer.
Thanks, Arnold. I mean, let's try and move through some of these questions. So Daniela asked the question, I'll just read it out for you. Are there any plans to integrate analysis-ready data into platforms such as Google Earth Engine to make it more accessible? Good question. Anyone want to venture an answer to that? I'm not aware of it, but others might.
I can give, this is Arnold Dekker again, I can give a few comments on that. We have had discussions with Google about this, but the ARD processing that is required is pretty complex, and to implement that into Google Earth Engine will cost a lot of compute power. And discussions that I've had with Google, but others may have had different discussions, is okay, that's going to be quite expensive. That's not going to be a simple implementation of a few band algorithms. So that's a discussion maybe the community needs to have with Google.
And I would add, we have a proposal in through GEO for Google Earth Engine credits to address or work towards this. We'll know more in about a month.
Okay, thanks very much. Moving on then, so Ritsky's asked a question about the geographical controls on perhaps on atmospheric correction. Maybe ARD for water quality monitoring should consider atmospheric corrections based on geographical conditions such as tropical, subtropical, and or other. Does anybody want to respond to that?
If I may, I think that's a good idea in general, in theory, but it would significantly complicate the process. So at least the data we've analyzed, they're coming from various locations, not covering necessarily tropical areas, but we're hoping that one or two processes would give good enough answer in terms of aquatic reflectance on products. But it's a good suggestion.
Great, thank you. Igor also asked a question about the adjacency effect and its contribution to the atmospheric correction. Was this taken into account in the A62 approach?
We took it out. We didn't look at adjacency effects. There are obvious locations, small reservoirs, about 200 to 300 meter wide, that none of the atmospheric correction could get anything out like reasonable for aquatic reflectances, and so we decided to just drop those out. But A63, if it happens, we will look into that as well.
Thanks very much. Okay, so Emily Smell asked the question, would the World Bank be interested in ARD projects? We have had a discussion with them in the past, and they have a relationship with Google Earth Engine. The question is, would the World Bank be interested? Arnold, you've been having conversations with the World Bank, or Steve?
I would just add that the proposal I mentioned, the World Bank is one of the co-leads on that. So yes, they have been part of this discussion.
Great, good. I'm just trying to look for the questions rather than statements. So people, I think that's it in terms of questions. Unless I've missed anything. So I think what we need to do is think about an approach going forward now. I think that's been a really useful discussion, but we do need to think about how we take this forward. There are a number of questions here, but I guess people are going to be running out of time if they're not run out of time already. So how should AquaWatch take this forward? How should the AquaWatch community take this forward, particularly in terms of maybe trying to think about standardized approaches and so on? Paul, I see you're lit up there.
Yeah, hey Andrew, hey, it's Paul DiGiacomo. So just a comment, many of you are aware of our CIOS Coast activity, Coastal Observation Application Study Team, and many of you are actively aware and engaged with it. And I think that that's one opportunity to try to facilitate this discussion. We're working with Rob and with Brian, with Wiggis and the ARD folks, and particularly and Steve and amongst others, to bridge that land-sea interface and the interoperability of the data, and working with Ed Armstrong, et cetera. So, I encourage folks that are interested. That's one mechanism, I think, with the backing of the space agencies, that will be able to focus on some of these. Steve is leading one of the pilot. Steve Grubb's leading one of the pilot activities, looking at sediment loading, so particularly across the land-sea interface. So that'll be one. Steven Cigar, also in terms of some of the coastal flooding and applications. So I mentioned that, many of you are aware of it, but it's one opportunity, I think, for us to move this forward. But again, one opportunity of many.
This is Steve. I want to go back and I'm thinking of Karsten's slide where he talked about who are the end users and what are the requirements of the end users, and then kind of working backwards, if you will, to understand what the ARD requirements are. And just from the perspective of the folks that have given the ARD talks, again, I'm trying to understand what the community can do, or what the community should be working on, or providing inputs for this ARD in terms of, we talked about thresholds, but do we need to start at the end and work back? Or again, how do we proceed forward here?
I mean, just one comment, Steve, if I may. It's not the end users who need ARD. Just a little clarification. As you have seen, it's in the middle of the pipeline.
Right.
Yeah, but and to answer your question, I would say my point was we are pretty much Earth observation people. So we come from up to down, and we think, because we know what is the level 1, what is the level 2, and we know what should be done. This is fine. We can go ahead, and from Card4L we have, I think, a template which is 60% okay, and we can take it. But to modify it and to adapt it to aquatic, we should spend some time to also analyze the demand side. So who are really the people who will work with these surface reflectances, and what do they need? And if we combine it with our knowledge from, let's say, the technology push side, then we will do a good job. So I would not stop and just focus on the users of ARD, but work on both sides. And then what I was reading in the chat, this comment on World Bank, and that they are really interested in the interpretation-ready products. That's an important aspect, because this is the end of the pipeline, and whatever we do, it has to lead to IRD. So I think this is a good extension, and that we really work on the whole pipeline to get the ARD right.
But as
Steve,
we describe it, sorry, go ahead.
Oh, I'm sorry. This is Brian Kill. I was just going to throw a few thoughts out there, some things I've experienced. I would say the broadest user base that we could support are countries around the world interested in answering the call for the Sustainable Development Goals. And so, you know, buried within the SDGs are a number of water quality, you know, products and parameters that they need to report on. So to me, that's probably the broadest audience that could use this. You know, certainly if you're thinking about a user focus for the, you know, high performance researcher and the people that use this data all the time, in many cases, they might have their own cookbook routine and their own favorite algorithm per se. But to have the broadest impact, if we could get the right data in the hands of some of these global users, it would be great, because in the meantime, I see them doing a lot of strange things, you know, using Landsat data with normal surface reflectance and using, you know, their favorite algorithm they found on Google Earth Engine. It's just a mix of stuff and not really using what I think this community would deem as an appropriate and accurate approach.
I think that's a really important point. It comes back to the opportunity here for us perhaps to flag up the appropriate ways to maybe provide a standard or an acceptable methodology for doing this type of work, and that's maybe where the AquaWatch can actually make a useful contribution. I'd also just emphasize that in terms of intergovernmental agencies, clearly the global approach is very useful in terms of global assessments. But again, at the national level, even countries wanting to report on SDGs, I think they would want to do it themselves if at all possible. I think they want that autonomy, and I think, you know, providing analysis-ready data is a good stepping stone for them to take on that capability as well. So there's a real capacity building opportunity there.
And if we as a community can guide that a bit, right, and provide what we think is the minimum set of requirements that achieves a quality, you know, data set, then at least they have knowledge of what the broader science community thinks is appropriate. And if they choose to use something else, they could certainly assess it against these ARD specifications, but they would know what this community thinks is appropriate.
Exactly. Yeah, I think that's a really important point.
This is Emily. So I just wanted to bring up one potential opportunity regarding the recent discussion. I was at a workshop a couple months ago now for a project that a UN agency, the International Atomic Energy Association, is funding on implementation of SDG 14.1.1, which is coastal eutrophication and marine plastics. And they are incorporating all aspects of SDG 14. I think the only requirement in terms of the IAEA is that there is some radionucleotide incorporation. But there were a lot of researchers there from the countries who are participating in the project, which was 15 countries from Latin America. And they were asking a lot about these specific questions that have been brought up. Which data set should I use? What do we need to do to tailor it to our region? I don't understand why this one product works better in my bay than this other product, and things like that. And so they were really interested in doing some test cases and potentially being involved in on trainings and whatnot. So that might be a community that could be an opportunity for doing a test case.
Okay, thank you, Emily. again, I'm conscious of the time, and I'm also conscious that people are dropping out as well. Steve, do we want to try and identify a group to try and take this forward?
Yeah, I agree. We're starting to run long here, and obviously we're not going to solve these problems today, but it was, again, just to spark some discussion and thought about it. And we were hoping, you know, from this initial community discussion that we could form a group. And I'll let Mary Beth take over this. So this is the last item on the agenda here in terms of soliciting participation.
Sure, I just put my email in the chat. It is mbeely@goaquawatch.org. If you would like to participate in a future focused discussion to take ARD to the next level and come up with minimum recommended standards, please email me and I'll schedule a meeting coming up, perhaps in 2 weeks. You can also put it in the chat if you would like.
And if you don't volunteer, I guess Mary Beth will be chasing you.
I will be sending out a community email. Hopefully it will have the right meeting address the next time for everyone to join.
Yeah. My
I
hope
think
was,
good points have come up, and I think we could maybe use that to structure a discussion to take this forward, actually, for another meeting.
right. This is an important discussion and an important topic. Has been highlighted here today, and yeah, my thought was we would have reform some sort of ad hoc committee within AquaWatch that would focus on this particular issue, or ARD and the issues surrounding it.
Absolutely. I'm not sure we have multiple committees at this point, so maybe we'll form more committees after the first discussion. But if anybody is interested in participating, you know, maybe you want to lead a charge in a certain area, you can include that in your email as well. I'm sure we could have that next meeting within the month, the next coming month, so that we don't lose momentum.
Yeah, we need to keep the momentum going on this one. Yep.
Okay, great. Thank you for that. Any other final comments or observations before we sign off here? I just wanted to thank everybody for taking the time. I know, believe it or not, during this COVID crisis, people are busier than ever, it seems like, and there's multiple meetings, and I appreciate you all taking the time today. And again, we would really appreciate your participation in this committee. Moving forward, we think this is a really important issue for our community, and it's important that we do this right. So with that, I think we'll go ahead and sign off. Thanks again.
Thanks,
Steve.
Thanks everybody.
I will also try and post the talk when it's available on the GeoAquaWatch website.
Great.
Thanks, everyone.
Thank you.
Okay, thank you. Bye-bye.
Thank you. Bye-bye.
Hey, Carol.